Hi, this video will be about homeostasis, specifically negative feedback and the two forms of negative feedback, long distance negative feedback or short distance negative feedback. So I wanted to remind you what negative feedback is. The purpose of negative feedback is, of course, to maintain homeostasis. We did a couple of examples last time. The example in your textbook involved basically trying to get a car to stay at 60 miles per hour, which is the set point you set for the speed. But as you start going uphill, the speed drops and there's an error signal sent between the measured speed and the set speed, or the actual and the ideal speed. And then what happens is you institute a change, this time by pressing on the gas pedal to get it back up to the set point. So that's a general example of a negative feedback not in the human body. And so what we're going to do today is we're going to look at a couple of examples in the human body, more than a couple, that fit into two different categories. So there's what we call extrinsic regulation, which we're going to cover first. It is a form of negative feedback that's generally, often, not always, but a little longer distance. And then there's intrinsic regulation, which is usually a little shorter distance. So let me give you an idea about what we're talking about. So if a problem occurs in the human body and the tissue or the organ or even the organ system in which it occurs, that tissue, organ, or organ system has the capacity to correct it back to homeostasis, then you kind of fixed it in-house and it's intrinsic, okay? And the other part of the metaphor would be extrinsic regulation. Extrinsic regulation is if something happens in an organ, a tissue, a body system, and that body system doesn't have the capacity to fix it back to homeostasis. So it calls on other body systems to help with that. That is called extrinsic regulation. So the metaphor, I don't know how many of you guys watched The Sopranos or some kind of, I don't know, crime family drama. So if Tony Soprano was a crime boss, a fictional crime boss, and so the metaphor I'm going to go for here is if someone breaks into my home, I am going to call the police to come investigate, help me solve this problem. So I'm using extrinsic regulation. Whereas if somebody broke into Tony Soprano's house, he's probably going to handle that in-house. And so that's intrinsic regulation. Hopefully that metaphor will work for you. So let me give you, instead of metaphor, some actual examples in the human body. So let's talk about extrinsic regulation first. So with extrinsic regulation, generally speaking, the two body systems that you are going to use to call in the troops to help you with a homeostatic need that you can't do yourself are the nervous system and the endocrine system. There are a couple of examples we'll run into later this semester in which I use another body system, but a good general rule is if I'm using the nervous system or the endocrine system to help and the problem didn't occur with the nervous or endocrine system, it's probably going to be extrinsic regulation. So it's usually slightly longer distances. The objective is still the same here. The objective is still to maintain homeostasis. So let me give you a couple of examples. So first, extrinsic regulation to accomplish negative feedback in order to maintain homeostasis. So you are an 11-year-old kid and you go trick-or-treating. And you get 6 full-size Butterfingers, or let's make it even better, 6 full-size Reese's, or whatever your favorite is. And you go home and you have siblings. So my question to you, or my question to me at 11 would be, where's the safest place to keep those 6 Butterfingers or those 6 Reese's? And in my case, because I have a big brother, it was probably in my digestive system, but that's going to completely disturb homeostasis. So let's look at what's actually going to happen. So what you are going to have in this situation is you ate 6 Butterfingers. That was a digestive system disturbance, right? It was a digestive system problem. But can I fix the problem with the digestive system? Let's think about this. So what it's going to do is it's going to disturb, among other things, the glucose concentration in your blood plasma. It's going to go through the roof, but I was a healthy 11-year-old. I was not a type 1 diabetic, so it didn't kill me. I had homeostatic control mechanisms that worked just fine to bring it back down, but the disturbance of homeostasis did occur. And the high glucose concentration that you've got there was the disturbance of homeostasis. So did I solve that problem with the digestive system? No, I can't actually, for instance, poop it out fast enough to maintain my glucose concentration. So what actually happened is I needed to call on the endocrine system. So what happened is the high glucose concentration would cause the endocrine system specifically to release more insulin, a hormone, from the pancreas. And insulin goes into the bloodstream and it allows the excess glucose to enter into most cells in your body. And so what that does is takes the glucose concentration, which was high in the blood plasma or the extracellular fluid, and brings it back down. And the normal blood glucose is restored as the blood glucose level goes back down. Okay. And then the new glucose level, this is the important part. It has to be a loop. Otherwise, the low glucose would be just as much of a problem as the high glucose. So the new glucose has to feed all the way back, right? Negative feedback inhibition as the new part of the variable so that you can actually stop this. So the insulin secretion will stop as you feed the new glucose level back. So this is extrinsic because it was a digestive system disturbance that called on another body system for help, right? And it's negative feedback because your glucose level was high and you brought it back down. But let's just make sure that you guys actually understand that what makes this negative feedback is not because the glucose went down. It's not the directionality. It is the opposition. The glucose was high and you brought it back down. That's what makes it negative feedback. But would it also be negative feedback if, for instance, we did the opposite example? The glucose was, low and we brought it back up. So fasting occurs, right? People fast for any number of different reasons. Intermittent fasting has actually been shown to have some beneficial properties, especially for like insulin resistance. And then people do it for cultural and religious reasons and a bunch of different reasons. But regardless of why you fast, it's kind of a digestive system disturbance, a little bit different because you kind of, let's say in these instances, you chose it. But regardless, what it's going to do is it's going to disturb your blood plasma glucose level in the opposite direction. So this time it's not a high blood plasma glucose that's the issue, it's a low blood plasma glucose that's the issue. That's the disturbance of homeostasis. And again, I can't or won't solve it with the digestive system. Of course, in these instances, I could solve it by eating something, but I'm not going to solve it by eating something. So, what we're going to do instead is we're going to phone a friend. We are going to, this time, call on the endocrine system again, but we're not going to release insulin this time because insulin's job is to lower blood glucose levels, and that's definitely not what we want here. We want to get back to the homeostatic levels of blood glucose. So instead, we're going to call on the endocrine system, still the pancreas this time, but the endocrine system is going to release a hormone called glucagon, which I'm not sure if you've heard of before. It's not known anywhere near as widely as insulin. So glucagon is released from the pancreas. And what glucagon does is it goes to the location in the human body that I have a whole bunch of glucose stored, which is among other places, but the primary place is the liver. So it's going to go to the liver and it's going to break down the stored glucose in the liver. Glucose is stored in animals as glycogen. So it's going to break down glycogen and it's going to dump that glucose back into the bloodstream. And what that's going to do this time is it's going to bring the blood glucose level not down, but up. So the normal blood glucose level is restored. But again, this is important because you need to, now that the normal level is restored, you need to know when to turn all of this off. So now what I need to do is I need to feed that new glucose level back into the system with negative feedback inhibition so I know when to stop. So let's reiterate. Okay, so with this example, hopefully you can see that this is negative feedback. It's negative feedback because I opposed the direction that the variable changed. So in this instance, my blood glucose level was too low and I brought it back up. So that opposition or negation is what makes it negative feedback. Even though the level went up, it's still negative feedback because it's still opposing the direction of change. So what makes it extrinsic? What made it extrinsic is that I started it with the digestive system, but I didn't solve it with the digestive system. I called on the endocrine system, okay? I could also call on the nervous system, but I didn't give you any nervous system examples just in this first set of notes because they take a little longer to understand. But these are both extrinsic because they started with one body system and actually called on another body system to help solve it. So that's like me calling the cops when my house is broken into. Okay, so now let us look at the opposite, well, not the opposite, the other type of negative feedback, and this is called intrinsic regulation. And intrinsic regulation is I have a problem in a tissue, organ, or body system, cells, whatever, and I can handle it in-house. So it tends to be shorter distance, and I don't need to use endocrine system, and I don't need to use nervous system to do this. So the activities of cells, tissues, organs, organ systems change locally or automatically to maintain homeostasis. Intrinsic regulation is sometimes also called auto-regulation, as in self, or local regulation, because of course it's more local. And it's usually shorter distance. Okay, so let me give you an example of intrinsic regulation. So there's going to be two. The second one's a little bit more complex, and we'll slow down and do that one. Okay, intrinsic regulation to accomplish negative feedback. So you've got a tissue that's really, really active for whatever reason. This one tissue is really, really active. Let's say maybe it's your liver that's really metabolically active. The rest of you isn't doing anything. Maybe yesterday, right? Maybe yesterday you took too much acetaminophen and your liver is busting its little liver buns off. Or maybe you did 6 shots of tequila. Either way, it's going to be really hard on your liver, and the rest of you might be laying on the couch not doing a whole hell of a lot. So my point about saying that is that I'm not saying the whole body is going to have high metabolic rate, just local area. So an active tissue has a high metabolic rate. And because of that, the cells in the tissue need more oxygen. That is the disturbance of homeostasis, is that the oxygen level is too low. The activity level is really high, you're using up your oxygen level drops. How can I handle this locally? I don't need to increase the heart rate because the rest of the body really isn't dealing with low levels of oxygen. So what happens is the cells in just that particular tissue will release chemicals that cause local arterial dilation to that tissue alone. And what that's, of course, going to do is to increase the rate of blood flow into the area, and therefore the oxygen level will go up in the area. Oxygen level rises in the tissues. Again, it's also important that as soon as it gets where you need it to be, you again do negative feedback inhibition. The oxygen level rises in the tissues. You're going to feed that back in as the new data point, and you're going to get negative feedback inhibition that tells you stop releasing those dilators. Okay, so that is homeostatic, right? Low levels of oxygen brought it back up. It's negative feedback because it opposed the direction it was going. The oxygen level was too low and you negated it and brought it back up. And it's intrinsic because I didn't phone a friend. I did it myself. Okay. All right. So that is the extrinsic example, the easy one. Now I want to do the harder one. So I'm going to introduce you to this chemical equation. In physiology, in my physiology class, you don't have to memorize a whole heck of a lot of chemical equations, and you don't have to balance them for me, because you can do that in chemistry, but you do need to understand them. So before I get into this example, I'm going to have to show you something that you may or may not have learned before. I'm going to show you what we call the bicarbonate buffering system. So I'm going to show you this equation, and then I'll tell you the story that goes with the equation. So let me just start the whiteboard. Okay. Ready? Okay, so you are going to have to memorize this. I know it might take you a minute, but you're eventually going to have to memorize this. So carbon dioxide plus water yields carbonic acid, which is H2. Oops, sorry. Wrote my 2 in the wrong place. CO3. And carbonic acid will dissociate to the bicarbonate ion, which is HCO3 minus, and a hydrogen ion. Okay, so why do you care? This means that there is a relationship between carbon dioxide and pH. So let's see if we can figure out what that relationship is before we go any further. So the relationship between carbon dioxide and pH is, typically speaking, that as your carbon dioxide, this is not a chemical equation, I'm just showing you a relationship. As your carbon dioxide goes up, what it tends to lead to is your H plus concentration goes up. And then what is the relationship, guys? As hydrogen ion concentration goes up, does that make the pH go up or the pH go down? So what does that do to your pH? Anybody remember? Okay, so what happens is, as you increase the concentration of hydrogen ions in a solution, it decreases the pH. And last question about this is just, okay, if you decrease the pH, does that mean that more carbon dioxide makes tends to make a solution more acidic or more basic? So as your pH goes down, you become more acidic. Cool? Okay, so keep this in mind, and you're going to definitely have to write this equation right here in your notes, and we're going to use it all semester long. So it's always best to teach this in the first set of notes, because then you can really get used to it and start just getting in your head what carbon dioxide has to do with pH. Okay, so keep that in your mind, and then let's talk about what that has to do with this example that we're going to do. So we've got an active tissue, and it has a high metabolic rate, but this time we're not going to be so much concerned about the oxygen concentration as we are going to be concerned about the pH. Okay, so the carbon dioxide will rise. Your carbon dioxide concentration will rise as the tissue does more aerobic cellular respiration. You get a carbon dioxide as a byproduct of aerobic cellular respiration. And then, of course, we know that this occurs, that CO2 and H2O makes carbonic acid, which is H2CO3. So we got that. And then carbonic acid will dissociate to the bicarbonate ion, which is HCO3 minus, and the hydrogen ion. So this is all that in that equation. And so let's make sure that you guys can do this part. So what do you think about more hydrogen ions? Do more hydrogen ions, you choose right here. Raise or lower the blood pH. More hydrogen ions lower the blood pH. Okay, so do I need to phone a friend to help with this? Actually, no, it's interesting. You don't, because the change in pH alone will trigger an increase in H plus secretion at the kidneys. So as your pH changes, You do not have to do anything special to get the kidney to dump more of it. So the change in pH will trigger an increase in H plus secretion at the kidney, basically make you pee out more H plus. And then what will happen is the blood pH dropped, right? It lowered right here, we said, okay. And then I fixed it automatically with the kidney, and then the blood pH will rise again. And as the blood pH rises, I can feed that back so that the kidney will know that I don't need to do that anymore. Okay, so let's make sure that this example makes sense to you. All right, so with this example, what we are dealing with is, again, this is going to be a negative feedback example because basically the carbon dioxide made my blood pH drop, and I served to bring it back up. So that's what makes it negative feedback. And then what makes it intrinsic instead of extrinsic, I didn't have to call on the nervous system or the endocrine system to help with this problem. Kind of occurred and then was automatically fixed. Okay, so now a lot of us have trouble with pH. So I want to go ahead and tell you that interactive physiology, which comes with your textbook, or a digital version of the textbook, has a good animation. It's a little deep for you right now, but the first part of it's really good about acid-base homeostasis that can kind of get you started on it. So let me just show you what it looks like. It's right here, and it basically, I'll introduce you to it briefly.
The body has 3 ways of maintaining a normal pH range: chemical buffer systems, respiratory controls, and renal mechanisms.
Okay, so it will go through all 3 of those. If you want to watch it, it's 5 minutes long. The first one is probably pretty useful for this set of notes. By the end of the semester, you'll know all 3 of them. They just may be slightly beyond your level of knowledge or interest at this point. Okay, and then last thing for this video is just, so what do tissues do? Do they try to maintain homeostasis with intrinsic regulation or extrinsic regulation? And the answer is yes, both. So most physiological variables, whether it's body temperature or blood glucose or pH or whatever, have intrinsic and extrinsic regulatory mechanisms. And what do you imagine? Which one do you imagine would be faster and potentially cheaper to try first? So what do you think? If I was trying to control my oxygen concentration in a tissue, do you think it would be faster or cheaper to cause local vasodilation or to cause the nervous system to increase heart rate and respiration? So does it make sense to you that the intrinsic ones are usually worth a shot to try first because they're cheaper and they're likely to be faster? And then if that fails, quite often you have the capacity to try an extrinsic regulatory mechanism. Okay, we will see as sort of a theme in human physiology that the body tends to try to do the cheapest, fastest thing first. Okay, we'll stop there.